Today we will study about types of threads. In the last class we have discussed about the concept of threads, the difference between threads and processes, and also we have seen two examples of the threads in case of web browser and in case of word processor. So let's begin with the types of threads. So we have two types of threads. One is user level thread and another one is your kernel level thread. So let's begin with user level thread. So in user level thread management is done by the user level thread library. So there is a library of threads available that will be actually managing the thread management, which involves creation of thread, deletion of threads once the work is done or once the job is done, resuming or suspending the threads, and today we will discuss about the type of threads. So there are two types of threads, user level thread and the kernel level thread. So before we go into that, today we will discuss about type of threads. In the last class we have seen about the concept of threads, the difference between thread and processes, and we have also seen two examples of threads, how they are being used in the system, one in case of word processor and another one in case of a web browser. Coming to type of threads, so there are two types of threads, user level thread and kernel level thread. So let's begin with user level thread. So in user level thread management is done by user level thread library. A thread library provides the programmer with an API for creating and managing threads. There are generally two primary ways of implementing a thread library. The first approach is to provide the library entirely in the user space with no kernel support, and the second approach is to implement the kernel level library supported directly by the operating system. So when we talk about thread management, we are talking about the four basic thread management operation: thread creation, thread termination, thread join, and thread yield. Here the thread management kernel is not aware of the existence of the thread as it is a user level thread. The thread library contains code for creating and destroying the threads. So as you know, the thread management task is also about creating and destroying of the threads. So the thread library contains code for creating and destroying threads, for passing message and data between threads, that is between the parent and the child, for scheduling thread execution, and for saving and restoring thread context. As we have seen in case of process control block PCB is being saved when we switch from one process to another. So that is what the context we are talking about in this case as thread context. The application starts with a single thread. Some examples are POSIX P threads, Mac C threads, and Solaris T threads. So So that is about user level threads. Now let's go to kernel level thread. So in kernel level thread, the thread management is done by the kernel. There is no thread management code in the application area. As we have seen in case of user level thread, there was thread management in the application area. Here no thread management is available in the application area. Kernel threads are supported directly by the operating system as they are part of the kernel. Any application can be programmed to be multi-threaded. All of the threads within an application are supported within a single process. The kernel maintains contact information for the process as a whole and for individual threads within the process. Scheduling by the kernel is done on a thread basis. The kernel performs thread creation, scheduling, management in kernel space. Kernel threads are generally slower to create and manage than the user threads. So some of the examples are Windows 95, 98, NT 2000, Solaris 264 Unix and Linux operating system. Now let us look at multi-threading models. So there are three multi-threading models: many to one, one to one and many to many. So let us look at the first model, many to one. In many to one multi-threading model, there are many user level threads that is mapped to a single kernel thread. These are used on systems that do not support kernel threads. In this image you can see there are several threads that are mapped to the kernel thread, that is the user threads. In this example 4 user threads are mapped to a single kernel thread. It is efficient, but the entire process will block if a thread makes a blocking system call. If one of the thread makes a blocking system call, then the entire process will fail. Also, because one thread can access the kernel at a time, multiple threads are unable to run on a multiprocessor system. As you can see in this example, each of the thread is actually using the kernel thread. So this thread is using, the other threads cannot use. Once the second thread is using, the other threads have to wait. So that is why they are unable to run on a multiprocessor system. Example of such many to one model is green threads. A thread library is also available for Solaris. Next is one to one model. In one to one model, each user level thread maps to kernel thread. Examples: Windows 95, 98, NT and 2000 or OS 2. So if we look at this particular image, it will give you an idea of one to one model. There are several kernel threads and there are several user threads. So each user thread is mapped to a single kernel thread. You can see each user thread mapped to a single kernel thread, each user thread mapped to a single kernel thread, each user thread mapped to a single kernel thread. The only drawback of this model is that creating a user thread requires creating a kernel thread also. So when we want to create a user thread, we have to create a kernel thread also, and creating the corresponding kernel thread is a burden to the system and the performance of the application. Most implementation of this type of model is restricted to number of threads that is being supported by the system. Linux, along with the family of Windows operating system, implements one to one model. So that is the reason, that is creating of the kernel thread becomes a burden for the system, and hence the performance is reduced. Next model is many to many. Here allows many user level thread to be mapped to many kernel threads. So there will be many user level thread and that will be mapped to many kernel threads. Allows the operating system to create a sufficient number of kernel threads. Examples are Solaris, Windows NT 2000 with thread fiber package. So if you look at particular this image, you can see there are several user threads and there are several kernel threads. Now what you have to understand, that the number of kernel thread may be less than or equal to the number of user threads. it cannot be more than the number of user threads. As in this example, there are 4 user level threads and the kernel threads are 3. So the maximum number of kernel threads that can the system support is 4 or less than 4, but not more than the number of user thread. The disadvantage if we go for many to one model is that the developer create as many user threads as he or she wishes, and in the example of many to one model, the concurrency is not gained because the kernel can schedule only one thread at a time. Also, in one to one model allows for greater concurrency, but the developer has to be careful not to create too many threads within an application. On the other hand, this particular many to many model suffers from neither of the shortcomings of many to one and one to one model. The developer can create as many user threads as necessary, and the corresponding kernel threads can run in parallel on a multiprocessor. Also, when a thread performs a blocking system call, the kernel can schedule another thread for execution. That is the advantage of many to many model.